Hello aspirants, welcome back to my channel. Today I have got something super exciting for you, especially if you are gearing up for your entrance exam. In this video, we will be diving into the essentials of revision notes for chemical equilibrium. Alright, let's get started. I have broken down the key points, equations and the tips you need to know to ace this topic. So grab your notebook pen and let's make this revision session both effective and efficient. So let us start the chapter Chemical Equilibrium. I have divided the Chemical Equilibrium chapter into 3 pages and 10 points. So let us start. The first point is endothermic reactions. Reactions in which heat is absorbed. Delta H will be positive. Heat of product is greater than the heat of reactant. Then this is the graph of endothermic reactions. Next, the exothermic reactions. Reactions in which heat is released. Delta H will be negative and heat of product is less than heat of reactant. This is the graph of exothermic reactions. Now, some examples of endothermic and exothermic reactions. So, the examples of endothermic reactions are dissociation reaction, sublimation reaction, and vaporization reaction and photosynthesis. The examples of exothermic reactions are combustion reaction, neutralization reaction, and respiration. Some exceptions of formation reactions that require heat, that is the endothermic. The first is formation of CS2, formation of NCl3, formation of NO, N2O and NO2, formation of OF2 or O2F2. Now, the third point is equilibrium. So definition of equilibrium is it is a state of a process where measurable properties like temperature, pressure, color, concentration of the system do not show any change with the passage of time. Now the characteristics of equilibrium. The first characteristic is rate of forward reaction is equal to rate of backward reaction, that is RF is equal to RB. Now the second characteristic is equilibrium is dynamic in nature and can be approached from both the sides. Now the third point is equilibrium is not affected by any presence of catalyst. It help only to attain the equilibrium state at more or less time. That catalyst only help to attain the equilibrium at more or less time. Now the fourth characteristic is equilibrium can be attained in both homogeneous and heterogeneous system. And the last characteristics of equilibrium is at equilibrium the concentration of product and reactant become constant. So for this I have drawn 3 graphs. You can see that in the first, second and third graph we can see that the concentration of product and reactant has become almost constant. Now the fourth point is active mass. So active mass is defined as number of moles per time. The unit is mole liter inverse. Now for pure solid and liquid, molar mass and density does not change. So active mass of pure solid and liquid will be always 1. You must remember that the active mass of pure solid and liquid is always 1. Now the fifth point is law of mass action or LOMA. Consider this is a reversible reaction. A plus B gives C plus D. Now rate of forward reaction will be directly proportional to concentration of A and concentration of B. Now rate of backward reaction will be directly proportional to concentration of C into concentration of D. Now to remove the proportionality sign, we can write that RF will be equal to KF into concentration of A into concentration of B, and RB will be equal to KB into concentration of C and concentration of D. Now what is KF and KB? KF is equal to rate constant or velocity constant for forward reaction, and KB is rate constant or velocity constant for backward reaction. Now at equilibrium, what will happen? We know that RF is equal to RB, we have discussed in the characteristics. So RF is equal to KF into concentration of A and concentration of B, and KB is equal to concentration of C and concentration of D. Then KF by KB will be equal to concentration of C and concentration of D divided by concentration of A and into concentration of B. Now KF and KB is equal to K. K is equal to C, concentration of C into concentration of D divided by concentration of A and concentration of B. Now what is K? K is the equilibrium constant. So KF and KF divided by KB is equal to K, and K is the equilibrium constant. Now let us consider a reversible reaction. That is A plus B gives C plus D. So small a and small b, small c, small d are the stoichiometry of A, B, C, D respectively. So at equilibrium state, Kc is equal to concentration of C raised to the power stoichiometry of C into concentration of D raised to the power stoichiometry of D, and concentration of A raised to the power stoichiometry of A, and concentration of B raised to the power stoichiometry of B. So when we define K in terms of active mass, it is known as Kc. And when we define equilibrium constant, that is K, at in terms of partial pressure, then it is written as Kp. So Kp will be equal to partial pressure of C raised to the power stoichiometry of C, and partial pressure of D raised to the power stoichiometry of D, and partial pressure of A divided by partial pressure of A raised to the power stoichiometry of A, and partial pressure of B raised to the power stoichiometry of B. There is another term, that is the Kx. When we define K in terms of mole fraction, then it is written as Kx. Kx is mole fraction of C raised to the power stoichiometry of C into xd raised to the power stoichiometry of D divided by x of A raised to the power A and x of B raised to the power B. This is K in terms of mole fraction. There are some relations between Kp and Kc and Kp and Kx. So Kp is equal to Kc into RT raised to the power delta Ng, and Kp is Kx into P raised to the power delta Ng. So these are two relations between Kp and Kc and Kp and Kx. So effect of temperature on equilibrium constant. Let K1 and K2 be equilibrium constant at temperature T1 and T2. This is the Van 't Hoff equation. Van 't Hoff equation, we can write that log of K2 by K1 is equal to delta H divided by 2.303 R into 1 by T1 minus 1 by T2. So if delta H will be 0, then K2 will be equal to K1, that is always K2 will be equal to K1. Again, delta H is positive. If delta H is positive, that is the endothermic, then T2 is greater than T1 and K2 will be greater than K1. And delta H is negative. In case of exothermic reaction, T2 is greater than T1 and K2 will be less than K1. So these are some important points you should know. Now let us go to the next topic, that is the Dalton's law. So what Dalton's law said? That Dalton's law said that P of gas is equal to X of gas into Pt. What is P? P of gas. P of gas is the partial pressure of the gas. X of gas means mole fraction of the gas, and Pt is the total pressure. Now the last second point, that is the Lee-Chatelier's principle. So according to Lee-Chatelier's principle, if a system at equilibrium is subjected to any change of any one factor such as concentration, pressure or temperature, then equilibrium is shifted in such a way that to nullify the effect of the change. So this is the Lee-Chatelier's principle. Now, if in case of temperature for endothermic reaction, if we increase the temperature, then equilibrium will shift towards forward direction. If we decrease the temperature in endothermic reaction, then equilibrium will shift towards backward direction. For exothermic reactions, if we increase the temperature, then equilibrium will shift towards backward direction, and if we decrease the temperature in exothermic reaction, then equilibrium will shift towards forward direction. Now the second unit is pressure. If we increase the pressure, we know volume will decrease, so equilibrium will shift towards less gaseous molecules. And again, if we decrease the pressure, volume will increase, then equilibrium will shift towards more gaseous molecules. Now factors affecting equilibrium constant. If a reaction is reversed, equilibrium constant get reciprocal. If a reaction is multiplied by some constant, then Kc nu will be equal to Kc raised to the power that constant. Now when two equilibrium are added, their equilibrium constants are multiplied. Now number 9th point, that is the physical equilibrium. The first point is ice-water system. When ice is subjected to heat, that is the endothermic process, then we get water. What happens when it is an endothermic process and there is increase in volume, so the favorable conditions will be high temperature and high pressure. Now the water and water vapor system. When water is subjected to heat, again endothermic process, then there is increase in volume, that is gas. So the favorable conditions are high pressure, high temperature and low pressure. Now the last point, that is the reaction quotient. So what is reaction quotient? It is expressed in the same way for equilibrium constant, except the concentration may not be necessarily be at equilibrium. So let us consider this as a reversible reaction. So QC will be same as Kc. Concentration of C raised to the power C, D, concentration of D raised to the power D, concentration of A raised to the power A, concentration of B raised to the power B. QP will be same PC. This is in terms of active mass, and in terms of pressure, QC and QP. Now when we compare QC and Kc, if QC is equal to Kc, then reaction is at equilibrium. If QC is greater than Kc, then reaction will move backward, and if QC is less than Kc, then reaction will move forward. So these are some of the important points for the chapter chemical equilibrium you should know. Thank you.